Yeah, it's a big group. Thanks for coming. I was asked to kind of explain why we are here at the Gravitational Waves program, what we're trying to understand better, I think is the way Lars phrased it. So I would say the main thing that we're trying to understand better is the two-body problem in general relativity. Why? Well, so here's our two bodies, and they could be in a binary. They might be like black holes or neutron stars. And I think it's not news to any of you that binaries of black holes and neutron stars make gravitational waves that are seen by LIGO and friends these days. And we're trying to, even if we just assumed that general relativity was the correct theory of gravity at the relevant scales, for this problem, it's hard to get a prediction out of general relativity for how this binary, very precisely how it moves, very precisely what these waves will look like that will be measured. This is really like over a century-old problem. Like this theory was written down in 1915, but we're still working on solving it. And I will talk about some of the ways that we try to solve it. This is also just like the zeroth order problem. What if gravity is not described by general relativity at the relevant scales? Then we should have or modified gravity, making it even more complicated. I'm not going to touch on that at all, because there's still lots of interesting things even in this, even if general relativity is right. And yeah, so the most important things about the bodies in a binary are their masses. In fact, to a large extent, when they're far away, there's going to be some typical distance separating them, some speeds. When they're far enough away, all that really matters is their masses, at least in general relativity. But when they get a bit closer, or when you look in more detail, other things like, for example, if these bodies are spinning, that becomes an important and very rich effect. It's also very hard to model. There could be tidal effects involved, especially for neutron stars instead of black holes. Like these bodies become deformed from the fact that they're in a non-uniform gravitational field. That has an effect on their motion, an effect on the waveform. Or related phenomenon of absorption. Sometimes, for example, black holes can eat energy from the gravitational field and increase their mass. This is another kind of effect that shows up at one point or another. And I should make it clear. So obviously, one approach to solving this problem is, if you will, so I'm going to call it numerical relativity, which is the name for essentially putting the four-dimensional partial differential equation that is Einstein's equation more or less on a supercomputer in its full glory and solving it with appropriate initial conditions that look like this and get these things to orbit, in spiral, merge into a single object and the gravitational waves that come out. Okay, so that is, in our workshop, there are a couple, or at least one guy. Couple, yes, thank you. Sebastiano, where's Sebastiano? At least a couple that come to mind of people who work, among other things, on that effort. Most of us here are what some people call the alternative analytical relativity, where essentially we're doing various different kinds of perturbation theories. So if there is some small parameter in the problem, we want to exploit it. Most of us here are working in various perturbative approaches. What are the main three perturbative approaches? So first, I'm just going to write some names. The most relevant one is Post-Newtonian. Henceforth, Pn. And essentially what we assume is, so an important parameter is the speeds involved in the binary. And if it really is a bound binary, we know that that v squared is of the order of gm over r. Actually, let me change this and define a little bit of notation. Capital M for the total mass m1 plus m2. This sometimes goes by the name of the Virial Theorem. Like if it is a bound orbit, or especially if it's a circular orbit, one of these is minus a half the other one. But we can assume that this is small compared to the speed of light squared. This is the basic assumption in the post-Newtonian approximation, which is the most relevant approximation for bound binaries. And there's a very long history of trying to solve the general relativistic two-body problem in a post-Newtonian expansion, going back to Einstein himself. And even before I start talking about the gravitational waves, which honestly, I'm not going to talk much about the gravitational waves themselves, but focus really on the motion of the binary. And corrections, so if we send the speed of light all the way to infinity, basically we know gr becomes Newtonian gravity. And we know how to solve the Newtonian two-body problem. It's basically the Kepler problem. And so then we're going to be looking for corrections to Newtonian gravity, or the Kepler problem, in a perturbation expansion where our small parameter is this divided by the speed of light squared. That's the post-Newtonian expansion. And as I said, the effort to solve that problem goes back to Einstein himself, and surprise, a little bit of preparation here. I'm writing down here a Hamiltonian for this two-body problem. So this is already intrinsically conservative. Just like in Newtonian gravity, gravity is conservative. There are no gravitational waves. Energy is conserved. And you might recognize, so it's a Hamiltonian. It's a function of a separation vector. So really here, you could say that's the vector that's pointing from one guy to the other. And say we're in the center of mass frame already. And two more pieces of notation you might recognize. Sorry, that should have been an equal sign. In Newtonian physics, we often define this thing, the reduced mass. The product of the masses over the sum of the masses. So I'll call that mu, the reduced mass. One more piece of notation. That, let's say, is this number nu times the total mass. So nu is mu over the total mass. That's called the symmetric mass ratio. Okay, I'm using these things down here. There's a position vector. And you can get equations of motion for that position vector from the standard Hamilton's equations from a certain Hamiltonian. And the Hamiltonian is just the total energy in the center of mass frame. It's the kinetic energy, which looks like the momentum. The relative, this is a momentum which is conjugate to that separation vector. It looks like the kinetic energy of a particle with momentum p and mass, the reduced mass. That is the kinetic energy in the center of mass frame. you can show this kind of equivalence. And the potential energy, which this is the same as G m1 m2 over r. Okay, so that's the Newtonian answer, if you will. Of course, you have to solve the equations of motion. The answer is ellipses, etc. That's the Newtonian problem that we want to perturb in powers of this small parameter. And here's the answer, one way to write the answer. And this is the so-called first post-Newtonian corrections. They come with 1 power of 1 over c squared. Like this whole thing should have units of energy. This you can see is like a speed momentum over mass to the 4th. So that's a speed to the 4th divided by speed squared. So this is mass speed squared. That's an energy. And you see there's these 3 kinds of terms, which is like a relativistic looking correction to kinetic energy, but then mixing with potential energy and like non-linear potential type terms. So this is the first post-Newtonian correction to the Kepler problem, Hamiltonian. This was derived first in, actually, it's often called the Einstein-Enfeld-Hoffmann the Lagrangian, which is a Legendre transformation of this. It was thought for a long time that they first did that in 1934. Actually, it was first done in 1917 by Lorentz and Drost, but this was lost until much later. And then, so that was a long time ago, long before anyone ever thought about detecting gravitational waves. In the 70s, 80s, 90s, and especially with the discovery of the Taylor-Hulse binary pulsar, which seemed to be emitting gravitational waves, people got reinvigorated in this push to perturbatively solve the two-body problem in general relativity. And even just to get to this second post-Newtonian level, which has a 1 over c to the 4th, and you can, I hope, see the structure. I didn't write out all the coefficients this time. There's just 2 terms missing. That happened. Ask the audience, when was that solved? Just in case I have the wrong decade in my head. Some of my colleagues. I think it wasn't finally settled until the 90s, the 1990s. Correct me if anyone knows better. And I should probably give you some names for that, but if you'll forgive me, I'm not going to do that. Maybe some more names.
But it was an implication of this 1 over c to the 4th, because normal corrections were studied, right?
Sorry?
I mean, observation, any observation where you need 1 over c.
Okay, so this was relevant, for example, for the binary pulsar. Yes. Okay, not maybe for the at first, but especially in the decades that followed, they definitely needed this guy to accurately model the binary pulsars, even before LIGO. Yeah, instead of just writing a bunch of equations like, yes, physical effects already, what kind of interesting things happen here? Well, this line, for example, gives you the precession of the perihelion of Mercury, which Einstein himself predicted and used to shape general relativity, the fact that he could get that right. Yeah, so for example, when you include the first relativistic corrections, the ellipses are not closed anymore. Like in the Kepler problem, the orbit precesses. That happens here already. That also happens in binary pulsars, and this is measurable. Continuing, I want to say, and I'm skipping lots of details and simplifying lots of things, but, and how much time have I already used? Okay. 3PN was settled like basically in the next decade. 4PN, kind of, let's say, it's still not actually done in completeness. And so how did all of these, how was this done? Right, so I'm going to talk about this, and this is just washing over many decades of really important and hard work, but I'm going to lump a bunch of this work, in fact, like all of the work up to here, was doing something what I would call traditional post-Newtonian calculations, where they're really like solving the field equations in position space and using only classical physics, but also very fancy math sometimes gets involved, to be contrasted with somewhere in here, there was a first wave of the idea to import methods from quantum field theory. Right? So we don't want to solve a quantum problem, but lots of nice calculational techniques have been developed for, for example, quantum chromodynamics, etc., or LHC physics. These started to be imported, some certain methods. In fact, let me just give a name. Let's say using Feynman diagrams, or even if it's still actually just a classical calculation. And I'm going to put my first names here. Goldberger and Rothstein, I think, wrote a very important paper in the first decade of this century. I think it was 2008 or maybe 2005. Anyway, it was definitely that decade, stressing how useful organizing these kind of perturbative calculations in terms of Feynman diagrams could be. And that was that led to a lot of progress in these kinds of efforts. And then actually much later down the road, kind of finally getting to the question of what are many of us in our workshop doing here. Still with the idea of import methods from quantum field theory, like for example Feynman diagrams, but there was this kind of other branch of quantum field theory efforts, which I'm going to loosely give the name of, yeah.
In normal, say, QED,
Yeah.
we know that starting from searching for the
Quantum gravity corrections to this problem. You can, and people do. Is it relevant for LIGO? Almost certainly not. Although some people, there are ideas about how quantum things near the horizon actually could be relevant for LIGO. That's maybe a different thing, but yes, that in fact, people think about that. H-bar corrections to specifically this thing have been computed.
But even the recognition and absorption, it's also kind of would be maybe not written here, right? So this stuff is just in this way is also quantum, right? Recognition.
Right. You mean of gravitons leaving the system? Yeah. And in fact, it is useful even to get the classical waves. It can be useful to think of them as gravitons, or maybe coherent states of gravitons, even if the final answer is purely classical. I'm not sure. Okay, so I was saying amplitudes, what is that? And maybe just one more buzzword to go with that. On-shell amplitudes, and maybe one more buzzword, unitarity methods. Okay, and I'm not going to attempt at all to explain what is meant by that, except for the moment, it's something that I'm told is better than Feynman diagrams. Is that, will my amplitudes friends, is that incorrect, or? That's correct, I think, or that's what they say anyway. And I think I can see how there's a lot of truth to it. Maybe I had plans to draw how many Feynman diagrams you would need for a certain calculation versus how many unitarity cuts you need for that same calculation. I might get to that, but quickly running out of time. Yes?
Without asking you to actually explain what you mean by amplitude and unitarity.
Yeah.
So these methods that you've written on the right, should I think of those as mathematical methods to solve field equations when you add perturbations to some order in C? Or are these techniques that have something to do with the underlying physical problem you're trying to solve?
Right. Okay. I want to say, okay, it's definitely not tied to this 1 over C thing. And this 1 over C thing is the first of 3 different perturbation schemes that I want to talk about. And, okay, let me go ahead and mention the next one, which is an alternative to Post-Newtonian. Maybe throughout the talk, before it's over, we'll touch on that question. But maybe it will start to become clear if I mention the next one of these perturbation themes, which is just what if Post-Minkowskian. What if, so here we're assuming that the gravitational field is weak. And this one, we're still going to assume that. We're going to assume that Gm over r is much less than c squared. Gravitational potentials are weak. But what if the speeds were relativistic? So in a nutshell, that's the alternative post-Minkowskian approximation. Now you would say, okay, wait a second. I said, if it's a bound binary, then these things are of the same order. So what's the point in trying to keep all orders in V at a given order in the field strength, if you will? Well, that's a very good question. Okay, one answer is there is a physical situation where you can access this regime. It's just, it's not bound binaries. It's, and this is a big keyword, scattering. Let me draw a picture for gravitational scattering. So here we say we'll still have M1, M2. They come in from infinity, but then they get close, they deflect. And there could be some, say, scattering angle. I'm going to call delta phi, describing that event. So anyway, gravitational scattering can be in this regime physically. Right? So I could try to solve that problem to all orders in V at given orders in Gm over R. That's post-Minkowskian. Why? What does this have to do with LIGO? Is it useless for LIGO? Since for LIGO, these things are of the same order, why do all the extra effort to get all orders in this if only finite order in that? So that's a difficult question, but let me also stress here that even just thinking about scattering, just general, the exercise of thinking about scattering instead of just thinking about bound systems has already, in the past 5, 6, 7 years, led to important insights about the structure of this problem and the structure of these perturbation expansions, I would say. And I hope to have time to tell you about one of those insights. But just generally, why scattering? How can it be more insightful? Well, I want to argue in some ways it's cleaner because you start at infinity and you go in and something complicated happens, but then you go back to infinity and things are clean at infinity, which is a common theme, right, in quantum field theory. And we're talking about making contact with quantum field theory and these amplitudes that I was talking about. I mean, I forgot the important word. These are scattering amplitudes. Things come from infinity, something happens, they go back out to infinity. And that makes things much cleaner than, say, a bound system. And so even without bringing the quantum into it, I would say just rethinking about how to do these perturbative expansions while doing scattering, not just bound systems, has also, independently of anything quantum, led to insights into this problem. That's one of the reasons. And then that's maybe also an argument for why post-Minkowskian. So if scattering is relevant, and if in post-Minkowskian we can do, if in scattering it makes sense to do post-Minkowskian, well, let's do it. And, okay, maybe one more, is that in these kind of perturbative expansions, like how high do we really need to go? Is it really making any difference? Is this expansion even converging? Right, decade after decade, are we actually getting anything better? That's a very good question. And actually, I think the answer is technically no. It is not converging. But, there's a dream, let's say, of we want to resum. Can we get the exact solution in some useful form? Right, that's a dream. And so you can see post-Minkowskian is like a step in that direction relative to post-Newtonian. So can we resum this column? So that would be like the zeroth post-Minkowskian column. By the way, that's very easy. The answer is just square root of m1 squared plus p squared plus square root of m2 squared plus p squared, which is like the Hamiltonian in the center of mass frame that you would write down for something in special relativity. Can you resum the next column? This one, with that missing term that I didn't write. That's actually also very easy. So that's the first post-Minkowskian column. I'm not going to write down the answer for a Hamiltonian. And by the way, I don't know if this was actually in the gauge where that's true, but there is a gauge in which that's true. And in fact, a lesson that we learn, another lesson that just without bringing quantum into it, thinking about scattering teaches us, is actually this kind of Hamiltonian thing is not a good thing to base your life around. It is a gauge-dependent quantity. I just mentioned this fact that I'm not sure what gauge, whenever I looked this thing up, I don't know what gauge it's in, but there's some gauge freedom. I can do canonical transformations in this Hamiltonian, and then it brings a question, and like this is often a big emphasis here, is like, can you organize your calculations in such a way that you only work with gauge invariant quantities?
But when you're looking at gravity, you always gauge fixing, because it's our basis.
Yeah, and lots of my traditional PN friends would argue that gauge freedom is your friend, right? If it's convenient to pick a certain gauge, it makes calculation easier.
It's defined by the way of observation.
Yeah. Okay, so you might push back against what I'm about to say also, but there's a claim that, that there is, for example, specifically this function, which is supposed to describe the conservative part of the two-body problem, but I say it's gauge-dependent. It would be nice if there were a function that had the same information modulo that gauge freedom. A gauge-invariant function which has all of the same information. I say there is, and it is this scattering angle function. So like the problem is send in these two masses. So this is going to be a function of those masses. It's going to be a function of the relative velocity at infinity. And actually, otherwise, it is only going to be a function of the so-called impact parameter. So even if I had such a Hamiltonian, I get the equations of motion, I solve them, I can get this function. Okay, so a claim that, as far as I know, or at least even stating this fact that I'm stating right now, only happened 5-6 years ago, unless we're all just ignorant of where it's in the past literature, that all of the gauge invariant information of this function is in this gauge invariant function. Yeah.
We get this from the scattering phase shift, which is just the scattering amplitude, which is gauge invariant.
Scattering phase shift for wave scattering,
Yeah.
like in an iconal limit. Or
I'm not making a approximation, I'm just making a statement. This is defined in terms of the derivatives of the scattering phase shift.
scattering phase shifts for wave scattering. Yes. I mean, sure. And in some ways, I think it is obvious.
The classical thing is, the particle thing is just the Bernoulli derivative of the scattering phase.
Yep. That all sounds right. I'm just saying that among the people who were doing this stuff, this statement that I just made was news, important news, like 5-6 years ago. And again, it may well be obvious to other communities. And that's also part of the point here about like communities. Things that are obvious to one community are certainly not to others. And I mean, I absolutely agree that it is often just a matter of ignorance of entire communities. But that's why we should all talk more.
You could argue it's just inline lectures.
Okay, maybe. Maybe, yeah. Nonetheless,
this is actually not obvious. Yeah, cases. It's not obvious.
There are cases where it's not.
There are cases where this conversion is not obvious at all.
Whether it's inverted.
No, just because you embedded this on a specific scattering problem.
Yeah.
It's not clear if you can invert that to this property which apply to all possible classes.
if I may, it may be obvious, or and certainly in hindsight.
But I still don't understand.
What?
Because if you fix the way what you experimentally observe the scattering angle, you fix the gauge. Because it is your experimental condition which it is a reason they gauge dependent. But this gauge depends on your measuring devices, right? Once you fix what you call measuring device, you fix the gauge.
I would say not. Like, you know, at the gauge dependence, if you will, like, there's even more gauge freedom than the sort I'm about to mention. But say this first column, for example, was fixed to that. There's still gauge freedom in the rest of it. But you notice the rest of it goes to 0 at infinity. As R goes, yeah.
Feel silly, what is gauge freedom? How it is, for example, G menu, your metric tensor, okay, and you know that you can put enough condition to fix it. Right?
Yeah.
But I'm trying to say that once you fix experimental condition, you are free to fix this gauge. So then there is no gauge freedom anymore.
Right. Well, let's say our experiment, I mean, I know there's an extent to which what I'm about to say is not true. But to a large extent, like way up in this expansion, it is basically true that my experiment is happening at infinity, let's say. And I want to say that at infinity, space-time is flat. And there is no gauge freedom.
Okay, so then
But
delta phi is also fixed.
that's right. That's the point I'm making. Yes, that delta phi is the thing that's measured at infinity, and there is no gauge freedom in that. Whereas this Hamiltonian thing, right, it has all these pieces, these potential pieces that vanish when R goes to infinity, but for those pieces and how to express them in the bulk.
But gauge freedom is the reason in classical mechanics always, because you always
That's right.
define your variables.
That's right. That's right. And it's often useful when there is such gauge freedom not to work with quantities that depend on that, if you can alternatively work with quantities that don't. That's all I'm saying.
I was just saying classically.
Yeah.
I do think it's a trivial statement.
Yep.
It's just the action value of the staging going from the boundary conditions given.
Yep. I do not disagree at all. But I'm still saying this was big news 5 or 6 years ago to some people. Some people who've spent decades working on these problems. It was certainly big news to me 5 or 6 years ago also. But yeah, in hindsight and to other people, it was always trivial. That doesn't make it any less powerful, is I guess the point. Let's see, how am I doing on time? That was one insight I wanted to emphasize. Actually, I said there were going to be 3 perturbation schemes. I've got to at least mention the third one, which is, wouldn't it be great if we could work to all orders in both of these small parameters? But maybe, like, in general, we can't do that. You need some small parameter to do any kind of perturbation theory. There's one more possible one left to us. I'll try to fit it in. Actually, I'll erase this. So we have the dream of strong fields and relativistic speeds, but we need some small parameter. What if it's the mass ratio? What if one of the masses is much smaller than the other one? Okay, if you go all the way in that limit, you get basically, so I could first call this in parallel with the other two, let me keep it simple, post-geodesic, or post-test body, or for some people, probe. So the probe limit, or the test body limit of the two-body problem, let's leave out spin, leave out tides, all that stuff. In fact, so this thing again, this Hamiltonian I wrote down, if I send one of the masses to 0 compared to the other one, I'm setting that symmetric mass ratio, nu, to 0. I lose that term, that term, that term, all these nus, but everything else stays untouched. What is that? Well, that is, so go all the way in the limit. So m1 over m2 goes to 0. This two-body problem becomes geodesic motion in a Schwarzschild spacetime. That is the spacetime of a non-rotating black hole. So we can solve that problem. Like, if you go all the way in the limit, that's kind of easy again. Like, we know how to solve for geodesics in a Schwarzschild spacetime. Okay, but now can you perturb away from that? Get the corrections to geodesic motion in this small parameter, which is the mass ratio. So this is yet another perturbation scheme. It could go by these names, which nobody uses. Everyone calls it the strange name of self-force. Okay, another word that's associated with it is black hole perturbation theory. So it involves having your background black hole spacetime, say Schwarzschild, a particle, little particle going around, and you want to consider the perturbations to the spacetime caused by the presence of the little body. And it's often said that the field of the particle itself exerts a force on that particle itself, which makes it deviate from geodesic motion, which is where this name comes from. That's the self-force. That's our third perturbation scheme. And the insight, I might not have time to explain, but an insight that came out 4 or 5 years ago was a connection between, so Post-Newtonian is involved, but like maybe a way to think about Post-Newtonian is if I had Post-Minkowskian, I just have to re-expand in V over C to get Post-Newtonian. Okay, but there was an insight that came from thinking about scattering. Really, I mean, some people would say we didn't need anything quantum to gain this insight. Just thinking about scattering. But that's not actually how it happened. It was when these guys, it only happened after these guys got involved and gave a new answer. For example, very quickly, I said it's easy to do linear in G, all orders in V. I don't know, I'm going to say that was done in the 70s. To do the second order in the Post-Minkowskian expansion, which would be like resumming this column or in some form. In fact, to give this function at G squared. That was done in the 80s. Then this Post-Minkowskian thing was dropped. And everybody was working on Post-Newtonian, and LIGO was happening. LIGO was being built. Until people, 5-ish years ago, people were making connections here, thinking about scattering, and someone, Thibaut Damour, actually called for these people to compute 3 p.m., and they did it. And that happened in 2019. Kind of, or part of it. And then in the next couple of years, they kind of finished it. But let's say the first result happened in 20, and I should put one name. That was Speedburn and collaborators. Some of those collaborators are in the room. Okay, so what? This, sorry, I'm mixing things up, but this is for arbitrary masses.
Yeah, so including zero mass.
Including, yeah. Which we already knew, that's just the Post-Minkowskian expansion of Schwarzschild geodesics. Oh wait, do you mean like massless, like null? Whoa, okay, yeah. Okay, yeah, no, well, what I really said, I didn't say one of the masses goes to 0. I said this goes to 0. There is a very important distinction. There is a very important distinction, which is also a whole can of worms with this result. Like this result does not, or this original 2019 result had a problem with the limit of actually taking, so maybe you're even aware of it already. Yeah, there's a big issue with that this, what I would say is the probe limit or the test body limit versus the massive to massless limit. They're not the same. It's an issue. It's a very interesting issue. Okay. But I'm supposed to finish in -3 minutes. And I wanted to say, no equations. I had a nice equation, but this insight that I wanted to talk about was the fact that when you look at this Hamiltonian, right, and I mentioned, okay, the test body limit is set nu to 0. It looks like I don't lose any information here at the Newtonian level. But it looks like I lose information at this first Post-Newtonian level. That I would need first order in the mass ratio or first order self-force corrections to get first Post-Newtonian right. And notice first Post-Newtonian goes up through second Post-Minkowskian. Okay, so I said that is the Hamiltonian and its gauge-dependent obscuring things. And in fact, if you just take this Hamiltonian and compute this function from it and express it in terms of those variables, you will find, I think I can remember this off the top of my head. Ooh, nope. But this is one of my favorite formulas. 2 is 1 plus v squared over v squared. That is the first Post-Minkowskian answer. So we knew that would include the Newtonian level. The second Post-Minkowskian answer is plus 3 pi 4 v squared plus, no, 4, what? 4 plus v squared over 4 v squared times g times the total mass over the impact parameter. And then the last thing I have to define, what do I mean by this E? It's the total energy in the center of mass frame. C equals 1 now. Okay, but the point is, there's no dependence on the mass ratio here in this function. And the next level, so I will say, this is the last thing I'm going to write down. When you think about scattering, when you reorganize things in a way that makes sense with special relativity, you realize that these first and second post-Minkowskian, so that is linear in G, formally post-Minkowskian is expansion in G, Post-Newtonian is expansion in 1 over C. Okay, forget 1 over C. We want to do everything relativistic. C equals 1. We're expanding in G. These you can get from what we would analogously call zeroth order self-force, or that is the test body limit, the probe limit, geodesics in Schwarzschild specifically. If you organize it right, you find that all of the information of this is actually in Schwarzschild geodesics. And furthermore, that if you could do just first order corrections to that problem, you would get the next 2 orders in the post-Minkowskian expansion, g cubed and g to the 4th. If you could do this somehow. And by the way, this has been known for 3-4 years, and it still hasn't been done to actually produce this answer. And by very different kinds of methods, these people are still working very hard to produce that answer from their better than Feynman diagram stuff. So it's not obvious. It's certainly not obvious from like the way I wrote it on the board. I could write it maybe in a different way that would make it more obvious. But let me just say, and I'd be happy to talk about it like after the talk, but let's say you do the problem in Schwarzschild, right? So, and you'll get some answer. The only thing that changes for the Schwarzschild answer in what I wrote down is that E becomes, I'm going to call it big M, but now when I'm in Schwarzschild, what is big M? Big M is just the mass of the Schwarzschild. So say I do the Schwarzschild problem, find the scattering angle for Schwarzschild geodesics. It's a function only of the Schwarzschild mass, the velocity, and the impact parameter. That's the answer. Now, separately, somewhere else, you do the real and much harder two-body calculation with the nonlinearity of gravity involved and with all the physics. What's the answer? Well, it's what I wrote down. Okay, so I'm not just like non-trivial information did not change. Okay, how did I know? How do you know that you need this factor of E outside? It's actually also quite simple to explain, but just comparing these two formulas for this quantity, which it's easy to explain what this quantity is, you can see, well, like basically the answer is there. Okay, I know that's not a very good answer, but the amplitude for the process makes it abundantly clear that, okay, and remember, in the two-body answer, I'm kind of hiding here. I used my definition of big M is M1 plus M2. So another way to think about this, in the amplitude for the process, or let's say, if you also wrote down the so-called impulse, which would be like a change in the form momentum of one of the particles, and you do the real two-body problem and you solve it, you find like at the linear order, Well, first of all, that weird factor of energy is gone in that quantity, also in this amplitude for this process. And it's replaced by like M1, M2 as an outside factor. And then here you have something that, well, I mean, really its scaling is like, let's just say I factored something out and there's no dependence on the masses here. And then here you have the sum of the masses. But with all the same coefficients. And then when you think about, okay, taking the test body limit, because there's also like even if you just start trying to make an ansatz for this function, you know it has to have certain symmetries. In fact, it has to be symmetric under interchange of M1 and M2. That kind of already tells you that it can only depend on M1 plus M2. At this stage, where there's no other things like spins, for example. Spins make it a bit more complicated, but for this non-spinning problem, there's a very simple argument for kind of why it has to be this way. And in any case, it is that way. And similarly, at the next couple of orders, you find that, okay, the information is not still there in just Schwarzschild geodesics, but even linear and mass ratio corrections to Schwarzschild geodesics could get you these next two orders. And let's leave it there. Thanks very much for listening.
More questions?
Are there numerical relativity simulations for scattering? Yes. There was very, actually, I don't know if the new ones are published yet, but they're coming. Did Harald? When was that?
05, 06,
Yeah. So these, I mean, are the not recent ones. And also there was a paper with Thibault and Seth Hopper and other people. Wait, were you on that paper? No. Yeah. There are simulations from numerical relativity scattering to black holes. Yes.
There's a lot of recent ones.
Okay, yeah, and there are more coming from. The first part of the question was convergence of these things.
Are they actually converging as you expect? Like, is the difference from the simulation order 0/6²?
So, specifically for the scattering simulations, or, I mean, you could ask the same question for normal bound binary, and how do they compare to post-Newtonian predictions? Right? Well, they agree very well in the earlier in spiral stage. But once it gets to the very end, and these black holes are going to merge, post-Newtonian has no prediction. It just completely breaks down. Because, I mean, that's when these things are both becoming one. So we expect it to blow up. And it does blow up. And it's useless.
My question was more
Well,
on the rate of convergence.
Yeah, they are simultaneous, so they are not converging as we expect.
To not so much to solve the comparable mass problem, but to solve the extreme mass problem, mass ratio problem, through this kind of connection that you described.
okay, that was a lot of points. And you at the end of your question, you kind of answered an earlier part of your question, which is like, or why not just do numerical relativity? Okay, why not just do numerical relativity? Well, as you know, and we're saying at the end of your question, there are parts of parameter space which numerical relativity cannot reach. In particular, very small mass ratios, like which will be, so extreme mass ratio in spirals, which will be sources for LISA, important sources. Numerical relativity just cannot go there because of the separation of scales, so we need something analytical or something alternative. Okay, even for the comparable mass problem, why do we want to keep pushing with perturbation theory? Okay, one, because it's fun, I say. Two, I mean, still, I mean, even though numerical relativity can reach parameter space. It's expensive to fill really the parameter space, and again, not the whole parameter space. So it's not accurate enough yet. It is very expensive, no matter how you look at it, numerical relativity. So if there's a better way, that would be great. And in fact, the best waveform models use both. Like numerical relativity is a crucial input, but like combined with post-Newtonian information is.
But we are still talking about kind of, and we understand if a parameter of expansion is small, indeed very small, then convergence, I would say, is not important, right? Until you're going for something which is non-perturbative.
Yeah, right.
So you are then implying that you are in the range where expansion parameter is not so small.
Well, that's what we want to push it there.
Okay, so let me, so Caitlin.
Yeah, so this is, I guess, building off of Ilya's question and maybe going back to my first question
Yeah.
a little bit. So I'm still not entirely sure what the problem is, not insofar as
Yeah.
I'm not trying to, I understand it's hard, I'm not questioning that. I'm trying to understand what makes it hard and what makes it unclear if we've solved the problem or not in given one of these limits. So very naively, when I think of perturbation theory, I think, okay, as we laid out, you decide what your small quantities are, you have the underlying equation, you write down the equation in that limit, and then you need to find a sufficiently rigorous mathematical solution method to solve it. So which is the hard part in this case? And I'm not questioning the 1 part percentage. I'm trying to get that. And then going back to Zoltan and Ilya's question about numerical relativity, if you don't have an analytic solution for much of the parameter space, as somebody who does numerical simulations that are non-relativistic, we often come at it the other way. We're like, we did this numerical problem. How do we know if it has any meaning? Well, we go to the analytic limit, we find the analytic solution, and then we check our code. So how do you resolve that ambiguity?
Which?
So I had two questions. And
Yeah.
The first question is, I don't understand why this is hard. I'm not questioning that it is.
Sure.
The second question is, how do you know numerical relativity is particularly reliable when you have no analytic solution to test against for a vast part of the parameter space, and you can't write down the solution even in some limits?
Okay. Again, I'll start with the second part. How do you know numerical relativity is good when you have nothing to compare it to? Well, you can compare numerical relativity to numerical relativity. Like, well, they do, they convergence tests, right? They have a resolution that can be adjusted, and then if you turn up the resolution, is it converging to something, or is it still? Yeah. Yeah. No, it's a very good question. And constraints. Yeah. There are consistency tests like constraints that have to be satisfied, although sometimes those are built into the code.
You can compare any numerical solution to any of these expansions,
Yeah.
and you will find that it gives
So
convergence.
so you're saying you're not putting the full field equation into your various simulation. You're using
These expansion also in certain limits.
Okay.
But of course you can compare the full equation in these limits.
Okay.
And you will see that the solution, the numerical solution will converge to the correct solution in the right limits. There are many techniques you can do.
Okay, so I'm going to leave some of these questions unanswered because we're going to go to Kavli in a minute. But please.
Oh yeah, sorry, I'll try to pick up. So sitting in the Newtonian side and looking out on the GR, all of this is within the context of the two-body problem. Thinking about the three-body problem is, of course, even complicated. You can use the Newtonian, but you can simplify it by making hierarchical systems and doing expansions, etc. So I'm curious as far as you have a waveform and you have data. Maybe you get lucky and you have some sort of hierarchical triple system. As far as constraining GR, are there ways to use these types of techniques in GR in hierarchical systems that might mix terms of different orders? Or is that
Okay, so the three-body problem, or hierarchical system, or which is a limit, an easy limit supposed to be of a three-body problem. Can we do that with GR?
how much of this carries?
Yeah, so just fun fact, these guys in 1934 They actually wrote this for an in-body system. And I just wrote it down for a two-body system. But so just the first relativistic corrections to Newtonian gravity for 3 or n bodies, these are known. And in fact, people also use them in numerical simulations that like evolve. In fact, in body systems, particle swarms. These are known. These are used. I'm forgetting again all the parts of your question, but for example, is this next level known for an in-body system? I'm pretty sure the answer is no, even still. Although I could be wrong. Do you? Yeah. And
last question. So the Post-Newtonian.
Yep.
I guess you're usually thinking of GM over R being small because R is relatively big, but
Yes.
if you let m go small, if you take the limit of m going small and v literally going to c, then it makes a black hole, but you know the answer in full GR, right? Because you can just superimpose Eckelberg-Zexel boosted pulses. Does that help you in any way? Like, can that be used to or is that just utterly?
That's a very good. Well, okay, yeah, Eichelberg-Zexel, which is this ultra-boosted black hole thing. Is this useful? Can this be used? Is it relevant? Probably. People are thinking about this. So this is related to this massless limit, actually massless limit, or going from time leg to null for these things. Is that relevant? Yeah, probably. And we mentioned already, interesting things happen, and like non-commutativity of that limit, like with the test body limit, even though they look very similar. There are interesting things that happen there. It's very subtle. I don't understand it. People are thinking about it. Is it useful? Probably.